Hey everyone, look around you. Everything we rely on this modern world, from finance to communication, is built on software. But there is one domain where the stakes are infinitely higher, where code can't fail and where hardware has to be absolutely, fundamentally perfect. Flight. We are not just talking about missions, we are talking about digital iron, the silicon that drives every modern wing and rudder. The aircraft of today are basically supercomputers. If a glitch happens in a website, it costs only money. If a glitch happens at 35,000 feet, it costs life. Today, we are going to strip down the process that ensures this absolute reliability. The next topic we are going to see in Unit 5 is Hardware Assessment, FAR's Guide, Certification Requirements, which comes down to a fundamental partnership between the law and the rule book. The law, which is the FAR, Federal Aviation Regulations, which issue the non-negotiable decree, "This shall be safe." And then the rule book, RTCA DO 254, the structured guide that dictates how we prove digital hardware is fit for the sky. In simple terms, we could say that here we are going to see how we build and certify the brains of the mission, making the safest form of travel on Earth possible. Let's dive in. First, the Federal Aviation Regulations, FAR. The FARs are the legal requirements set by the government, like the FAA, which are very important for the air safety. First, the core rule, FAR Section 25.1309. This is the ultimate safety requirement. It simply says that everything must work as intended, and if it does fail, it cannot cause a catastrophe. There are two primary requirements for this section. First, functioning under all conditions. The equipment must be designed and installed to perform its intended job under any foreseeable operating condition like extreme weather, high vibration, or electrical surges. Number 2, failure management. This is the core of the system safety requirement. It states that the airplane systems must be designed so that catastrophic failures are extremely improbable. Any failure conditions that would prevent the continued safe flight and landing must not be present in the system at all. Major failures are improbable. Any failure condition that would significantly reduce the aircraft capability should not be present. Now we have completed with the law, which is FAR. Since FAR only say be safe, the industry created the rule book, which is RTCA DO 254. This rule book tells us how to be safe. It's a step-by-step guide for proving complex electronic hardware is trustworthy. Here, as said before, there are set of steps to be followed. First, design assurance levels. The risk rating given. Not all parts are equally important. The DAL is a rating we give the hardware based on the risk of its failure. The higher the risk, the harder we have to test it. Here in this below tabulation, we can see the core decision matrix in avionics hardware certification. It links the component's potential for failure directly to the rigor we must apply in its development and testing. The DAL is essentially the risk rating of a piece of hardware. It's assigned during the system safety assessment based on what happens if the component fails. First, the top DALA, the absolute standard. This is reserved for the systems whose failure is catastrophic, meaning it could lead to a loss of aircraft and loss of life. To counter this risk, the required testing effort is maximum. We must provide near perfect proof that this system won't fail in a way that leads to a catastrophe. This involves the most expensive, detailed, and independent verification procedures. Moving down to the DALB and DALC represent failure consequences that are hazardous or major. While the plane may not crash immediately, the failure could severely complicate the crew's job or cause serious injury. The regulatory requirement here is still high to very high testing effort. We can tolerate a slightly higher probability of failure than DALA, but the design assurance still need to be exceptional. Finally, DALD and DALE are for systems that have a minor or no effect on the plane's ability to fly safely. Think of something like a passenger entertainment display. A failure here is mostly just an inconvenience, so the required testing effort is standard or minimum. We don't spend millions certifying a component that cannot compromise safety. The step 2 in DO 254. The 7-step process is a structured mandatory pathway that all critical airborne hardware must follow. The hardware life cycle, 7 steps to trust. We don't just build the component and cross our fingers. We follow a defined step-by-step process that builds evidence of safety at every turn. This process is documented in DO 254. First, planning, the strategy phase. This is where you write the master contract with the regulators. You decide the how will we design it, how will we test it, how will we document the proof. This step produces the foundational document, the plan for hardware aspects of certifications. If the plan isn't right, the certification fails before the first wire is drawn. Then, the second step, requirements capture, which is defining the goal. This defines the must-do list for the chip. Every function, big or small, is documented clearly. We need requirements that are precise and testable. Moving on to the third step, design and implementation. Here, the actual engineering work, creating the circuit diagrams and logic code and etc. The engineers build the hardware to satisfy every single requirement defined in step 2. The fourth step, verification and validation. Here, the crucial testing happens. This is the most resource intensive and critical phase where we break the component to prove its strength. Here, validation, which is checking the requirements, and then verification, checking the finished project. Here, we run thousands of steps to prove that the final hardware exactly meets every technical requirement from step 2. Now, step 5, configuration management, which is control and traceability. Here, the strict process of locking down and tracking every document and change happens. Certification is about traceability. The configuration management makes sure no unauthorized changes occurs and that we can reproduce the exact version of the hardware and its documentation at any time. The sixth step is process assurance, the independent audit. Here, an independent team acts as the internal regulator to audit the developers. Here, they confirm that the documentation is complete, the reviews were conducted properly, and etc. The seventh step is certification license, getting the final approval. Here, presenting the complete evidence package to the aviation authority. This is the final step where the engineers talk to the FAA or EASA regulator. If the documentation is complete and the evidence is solid, the regulator signs off and the hardware is deemed airworthy, which is ready to fly. Finally, the step 3 in the step-by-step process, the final proof, the paperwork. To prove compliance, 3 documents are the key. First, PHAC, Plan for Hardware Aspects of Certification. This is the contract with the FAA that outlines the entire compliance plan. And then, HVVP, Hardware V&V Plan. This is a detailed plan, shows how all the testing will be done. And finally, HAS, Hardware Accomplishment Summary, the final receipt. The document that summarizes all the work, testing and proof confirming the hardware is safe and complies with all the rules. Within this, we can conclude the topic Hardware Assessment FAA's Guide, Certification and Requirements. Thank you.